Hi, I'm David, and I'm here to talk about Egalito, our binary recompiler. So we're all quite aware that cyber attacks can lead to a lot of negative consequences, like financial fraud and data breaches. But unfortunately, it only takes one software bug to compromise an entire system. And software is full of bugs. On average, there are 50 vulnerabilities, 50 bugs per 1,000 lines of deployed production code. So it's kind of a lost cause to try to prevent all cyber attacks, but we can try to raise the bar much higher for an attacker. We focus on two main aspects. The first is to proactively guard against attacks, and the second is to retroactively fix vulnerabilities once they become known. So how should we fix memory access errors in unsafe languages? Well, with source level access, we could modify the compiler, or we could maybe rewrite all the code in a safer language. Neither of these is very realistic in many cases. So that's why we turn to binary level transformation. This is more deployable because every user has the binaries that are running the code, so they have the binaries. But changing binaries is very error prone and challenging. Binaries are not meant to be modified. And existing binary level modification techniques are either not powerful enough to do comprehensive hardening, or they just incur high overhead. So we have observed two trends in modern binaries that, that result in additional metadata for analysis. So the first is that binaries are doing a security trade-off to position-independent code. So position-independent code used to be quite expensive, especially, for example, on 32-bit x86, which has only 8 general-purpose registers. You had to reserve one register just to store the base address if you wanted to have position-independent code. But now, on modern architectures, including 64-bit x86, the program counter register can be accessed directly. So there's no need to reserve one of the registers for it. And as a result, position-independent code is quite good performance. And actually, over the past few years, compilers on a lot of architectures have switched to using position-independent code by default. This is to enable ASLR for executables. As I said, this is a security trade-off, and the performance downside isn't that great anymore, so that's why compilers have made this decision. The second trend we've noticed is that code gets written in several different languages. So you write some C++ code, it calls a C library, or vice versa. And to enable this interoperability between languages, we start seeing metadata in languages that don't even really need it. Like C code, for example, doesn't include, C code never throws exceptions, but right now, by default, it includes exception unwind information for every function. And this is in case C++ code calls C code, and you have, or other way around, I guess, and you have an exception thrown from C++. You want to be able to propagate that exception through C stack frames. So these two trends together mean that there's more metadata than ever before in modern binaries. So I'm going to go through how our binary recompilation works, how we do disassembly, and then some evaluation and a live demo. Binary recompilation is one of 3 ways you could do binary transformation. There's also code patching and process virtualization. So let's see what these 3 look like. This is some x86 code here. We are trying to take this indirect function call and check to make sure the pointer is not null right before doing the call. So let's use binary caching to do that. Well, we want to insert some instructions, but there's no space, so we erase something that's already there and we jump to a detour. Now notice that any function, one or more instructions that we erased have to get replicated down here inside the detour. And there's a lot of bouncing back and forth whenever we do some binary patching. With process virtualization, we can insert the instructions in line right here because the process virtualization doesn't try to keep functions at the same addresses. However, every time you use a code pointer, such as by calling a function pointer, you have to do this conversion between address spaces. So all the code pointer values are as they were in the original program. So it's like you're virtualizing the original program layout and the original address space. But in fact, you're running now at different addresses. So you have to do this conversion every time you use a function pointer. Finally, for binary recompilation, it's kind of the best of all worlds. So we're able to insert instructions here in line, and that's going to end up giving new addresses to every instruction, every function after that, because you end up shifting everything down. This is only possible if we found all references to func2, because if we missed some references to func2 and we didn't update them when we moved it to a new address, those old references are pointing somewhere in the middle of func1 now, which is obviously incorrect. So code patching is simple to implement, but it's not very well suited for large-scale changes. Virtualization, process virtualization, will work on any binary, but it does require this virtual runtime. And the binaries don't look much like ordinary binaries, so they're hard to debug, for example, and can have high overhead. Binary recompilation is pretty difficult to perform because you need precise analysis of all of the functions, pointers, jump tables, and so on in the binary so that you can change them in case they get moved to new addresses. This does give you the same power as the original linker or the original compiler backend, where anything can be moved to a new address. So this is what we're going for here, recompilation. Let me introduce Egalito. Egalito is a binary recompiler. It starts from binaries, lifts to an intermediate representation, and then outputs something that looks like an ordinary binary. There's no patching, there's no virtualization. I want to mention as well that the input is an ordinary modern binary. It can be a stripped binary. It's, for example, a binary that you might find in a Linux distribution's package management system. By design, Egalito is going to introduce near zero overhead. Like I mentioned, there's no patching and there's no virtualization. It's pretty much the same sequence of instructions in the output binary. So the overhead is nearly zero. Once you have that IR, Egalito allows you to do arbitrary modifications to it. There's no dependency on original addresses. That's why we call this layout-agnostic. The framework doesn't really care which address items are assigned to. These transformations, by the way, are done through what we call recompiler passes. And that's named after compiler passes, of course. Egalito uses very few heuristics. We're going to leverage those two trends that I mentioned earlier and see that there's more metadata, and so we don't have to rely on as many heuristics. And Egalito works on several different architectures. So this is what Egalito looks like internally. So this is actually a typical compiler on the right here, starting from source code, going through the compiler level IR, and outputting machine code. What Egalito does is it starts from machine code, lifts it to IR, where you can run the recompiler passes, and then outputs new machine code. So Egalito's IR is lower level than a typical compiler IR. The compiler IR is normally designed for optimization, so it's a little bit more abstracted. The Egalito IR is designed to represent every instruction encoding, so that you can change it or not, and then result in very similar output binaries to the original. There are two layers here, though. So this Egalito IR is the canonical level at which you can modify the code. We also have this higher level representation, which is sort of equivalent to a compiler level IR, like the LLVM IR. This is really good for doing analyses, like our own jump table analyses rely on it. But this is the canonical representation. All the changes have to happen here. So we think about this as sort of like LLVM for binaries. It has a similar design where it can be used to implement anything, and a lot of the functionality is in recompiler passes. A quick note about the name Egalito. It comes from egalitarian in two aspects. The first is that we're trying to make binary transformation more equal with source level transformation. Right now it's a lot easier to do things at source level. We want to make it more equal. And secondly, in a more literal sense, we consider something to be egalitarian if it, say, it can analyze itself, a defense that can defend itself. This is similar to compiler being able to bootstrap and compile itself. So our disassembly. Well, it's pretty well known that binary disassembly is undecidable. So that's why there's some dynamic techniques that try to tackle this, like dynamic binary translation. You start running the first basic block, and then you see where you get to, and then you fetch it from the program, and then you translate it, you go back and forth just in time. That works pretty well, but it can be slow. At the static level, you can try to under-approximate the code, over-approximate the code, or use heuristics to try to get at exactly the code that's in the binary. If you under-approximate, then you have to preserve the program layout in case there's some code you didn't notice. This is like the binary patching example that I mentioned earlier. If you over-approximate the code, you end up with a lot of sequences that are kind of nonsensical, so it makes a lot of analyses more complicated. However, finding exactly the code that's in the binary used to require a lot of heuristics and speculative disassembly. We're trying to get this same category here of finding exactly the code that's present, but we're not going to rely on those older techniques. So when you do disassembly with Egalito, first we'll distinguish the code in the data by looking at some simple metadata that tells us where the text section is. Then we're going to try to find all code pointers, and we leverage whatever metadata is present from position-independent code and use some data flow analysis as well. Position-independent code is extremely helpful in identifying code pointers. These are some global variables, for example. This number looks like it could be a pointer. It's within the valid range, but maybe it's also an integer. And if it's position-dependent code, you can't tell the difference. You have to speculatively guess one or the other. But if it's position-independent, and it's a pointer, there'll be metadata. The ground truth that says this is a pointer. Similarly, for code, in the code section, there could be a number here, which might be the bound of a for loop, or it could be a pointer. And with position-dependent code, you really can't tell the difference. If it's position-independent code, and it's a pointer, it will be added to the RIP register. It'll be PC relative. So yeah, the metadata really helps in finding all code pointers. Finally, we're going to try to identify all high-level constructs, like functions, jump tables, vtables, and so on. And function boundaries we find through the control flow graph, and we use the exception unwind metadata that I mentioned as the second trend at the beginning, if it's present. We do rely on a lot of data flow analyses because the metadata doesn't describe everything. The metadata wasn't designed to make binary analysis simpler. That's just a good side effect. It was designed for other purposes. And because we need to find all code pointers, sometimes it's not complete. In particular, there's a very tricky case on RISC architectures. This is ARM over here, where if you want to load a code pointer into a register, you can't do it with a single instruction because the instructions are short enough that you can't fit an entire pointer value into one instruction. So it gets split into two instructions. These are the upper bits, those are the lower bits. And the compiler optimizer will place these instructions arbitrarily far apart. And we need to identify that this is one half of the same value that this is, so that when we potentially move that target to a new address, we update both locations. So our data flow analysis will figure out that this flows into this. We also need to fully identify jump tables. We need to find the jump instructions, but also the locations of the tables themselves and the number of entries in those tables. Because if you don't, then the recompilation will have restrictions on not being able to move the basic blocks within a function, for example. And we don't want that. We want arbitrary modifications of addresses. Some evaluation. Let's first talk about Egalito versus DynamoRIO and Pin. So these are two fairly familiar tools, and they do dynamic analysis, so they have pretty high overhead here. Egalito, on the other hand, has almost zero overhead. And in fact, if we turn on some compiler optimizations, Egalito can get 1.7% performance improvement. So we just took the normal spec CPU binaries, lift them into Egalito, output a new binary, and it's faster than the original. So that's pretty cool. We also did a large-scale evaluation on Debian packages. So here we took 867 executables and libraries. We asked Egalito to analyze everything about them, including the function boundaries, the jump tables, the jump table bounds, and we were correct on all but one of those cases. In one case, the bound for one table was wrong. We actually checked this against the ground truth metadata. So we took the source packages for all those programs, we recompiled it to get the compiler IR, and we extracted from that IR the information we needed, such as the number of jump tables and the number of entries in each table. So that's the analysis part. For transformation, we tried to transform, 149 Debian packages that contained Debian level package tests. And unfortunately, only 60% of those passed right away with no additional effort. A lot of the failures, almost all the failures are due to engineering effort only. And there's one case in particular that's responsible for 40 failures. And that is that we support parsing symbol versions, but we don't support generating symbol versions. So we're working on that, and hopefully that will be fixed shortly. I want to mention as well that Egalito actually assigns new addresses to each function. So in this case, for example, we pick a new permutation and new offsets between functions, so that if Egalito parses a binary and outputs a new one, it has really understood everything that was in that binary. Because if not, then the new binary won't run properly. So we have actually picked a new address for every function. We also have a virtual machine image as part of the ASPLOS artifact evaluation, which is provided if you want to replicate some of these experiments. Lastly, I want to mention that our collaborators at Brown have been analyzing all of the Debian programs that are C, C++, and position independent, and there's 26,000 of them. And we are able to parse close to 97% of them correctly right now. So that's pretty cool too. We have a lot of tools implemented with Egalito that we discussed in our paper. Some hardware mitigations, some just ordinary software hardening, some miscellaneous ones as well. I want to point out the binary level fuzzing plugin, which is compatible with AFL, because it's up to 60 times faster than other binary level fuzzing. As I mentioned, binary recompilation is really efficient if you can get it to work. Let's talk a little bit more about these two hardware mitigations. Intel CET in particular is a security feature that will be available in future Intel CPUs, but is not currently implemented. So we have a software emulation before it becomes available in the hardware. So CET, that's what I was just talking about, and Retpolines, this is just a graph showing that you can run both of them on all of the spec CPU programs, and you get reasonable overhead. The Retpolines are 6.9% overhead, that's roughly in line with published numbers, and the Intel CET emulation is 4.4% overhead. So here's a Retpoline example of what it actually looks like to harden a binary with Egalito. The user will just say, Egalito harden, I want Retpolines, input binary, output binary. And what will happen inside the code is that, for Retpolines, is that every indirect call will end up being transformed into a direct call to a specific Retpoline. These are auto-generated, but they're deduplicated. So if there are multiple calls that do RAX, they'll all point to the same one, so that there's no wasted space in the output binary. So now what I want to do is my live demo, and this is a Spectre Variant 1 demo of the bounds check bypass. So this is a proof of concept that's available on GitHub. And what's happening here is we have an array which stores a secret, in this case, quick brown fox, lazy dog. And this is the program using a timing side channel to access the elements of that array. So the processor never issues reads to that array. Instead, there are only speculative reads into that array, which will then put stuff into the cache, and then you can figure it out from timing side channel. So let's see what that code looks like. This is the bounds check bypass Spectre Variant 1 problem, where you have a check, and then you access an array. So essentially, of course, the real code won't violate this bounds check, but the speculative execution will. It will just skip this bounds check and run this anyway. So if you want to prevent that from happening, you can put a memory fence here. So this is an example where there's a program, it's vulnerable, there's a user-controlled input, and the system administrator wants to prevent this from being used in a speculative manner. So they want to transform this binary to add the memory fence. So let's do that with Egalito. As you can see, it runs pretty much instantaneously. Here's the memory fence that we added. As you can see, this is binary recompilation, so these addresses got updated. We had to slide down all the instructions after this in order to insert the memory fence. So let's try running that program. And as you can see, a bunch of nonsense. Question marks, exclamation marks. If we run it again, we'll get something different. And this is showing that the timing side channel is no longer reliable just because of that memory fence. One last thing here. I want to show you the source code that's used to implement that. And it's pretty simple. We ask Egalito to look for the victim function, get the appropriate basic block, create a new memory fence, and insert that memory fence right before the first instruction of that basic block. So basically, this is all the code that's needed to implement that defense for this specific binary against Spectre Variant 1. So I want to summarize by saying, yes, Egalito can analyze and transform itself, and we've successfully run it on thousands of applications. The transformation overhead of the output binaries is near zero, and actually you can get a performance improvement if you're willing to turn on our binary optimizations. So Egalito is particularly useful for preemptive hardening or for retroactive patching of vulnerabilities once they're discovered, as my example with Spectre Variant 1 was showing. We have a lot of tools implemented with Egalito, including some mitigations for hardware features, software hardening, and some miscellaneous stuff, including an AFL-compatible fuzzing backend. So that's all I have for today. Egalito is released under the GNU GPL version 3, so it's open source. For more information, please go to egalito.org. And if you have any questions, please leave them in the comments. Thank you.